Hello everyone, welcome to my video on integration by parts. So this is our second integration technique that we're learning. We saw our first one, which is U substitution. U substitution goes hand in hand with chain rule. So in calculus 1 we saw chain rule. In calculus 2 we're looking at U substitution when we're dealing with the integral of a composition of functions. Now we saw product rule in cal 1, and the cal 2 equivalent is integration by parts. So whenever you're multiplying two different types of functions and you're trying to integrate this function, well, we're gonna attempt integration by parts. So it won't always work. Again, it's one of those things that comes with practice. My advice to you is always attempt U substitution first. If that doesn't work, then go ahead and apply integration by parts. So what does integration by parts tell us? So it tells us that the integral of f of x times g prime of x dx is equal to f of x gx minus the integral of gx times f prime of x dx. Okay, so that's the claim. I'm not going to prove it. Again, if you want to see the proof, let me know in the comments and I'll create a video on the proof on its own and I'll go through the details with you. But essentially it stems from product rule. A better way to memorize this formula is the integral of u dv, which is equal to u times v minus the integral of v du. So these two claims are the exact same thing. It's easier to memorize in this form. Okay, so let's go ahead and look at the strategy on how to solve integration by part questions. Again, the strategy is not foolproof. There's some situations where it won't work, but for 90% of the cases it's a good strategy to follow, especially at the beginning. So let's go ahead and take a look at that. So in order to solve integration by part problems, you first have to begin by identifying the integral is in fact an integration by parts problem. How? By noticing that you have a multiplication of two different types of functions. So if you have a multiplication of two different types of function, you should be thinking of applying integration by parts. Okay, we come across the same issue that we saw for U substitution, where we have to identify a U. It's up to us to choose a U. What do we let our U equal to? Well, in order to choose the U, one of the ways of doing it is to follow this acronym called LIATE, L-I-A-T-E. That's one way of remembering it, and this is the order in which you should choose your functions. So the highest order over here is 1. We have L, which stands for logarithmic function. So if you're dealing with a ln or a log function, that's typically your U. You're going to let U equal your ln or your log function. If you have a multiplication of two functions and one of them is inverse and the other one's log, well, log's going to win. Inverse comes second, so inverse, the I stands for inverse trigonometric functions. So if you're dealing with arcsine, arctan, that's in second place. So if you're multiplying a log function times inverse trig function, well, your U is going to be the log function. After inverse, you have A, which stands for algebraic functions, which is essentially polynomials, so x squared or x to the 4 minus x cubed plus 1. Well, if you have a battle between, or if you're multiplying a function which is algebraic function times a logarithmic function, well, again, logarithmic is above the algebraic function, so we're going to let U equal the logarithmic function, okay, because it's above. Okay, inverse versus algebraic functions, well, the inverse trig functions win over algebra functions, and so on and so forth. T stands for trigonometric functions, that's sine, cos, or tan, among the other ones, and exponential function E is the ones we want to avoid. This is e to the x or any number to the x. So when you're dealing with exponentials, typically you do not let your U equal the exponential function, but again, this strategy here is not foolproof. It doesn't work 100% of the time. There's problems where this might not apply, but again, 90% of the time, this is a good general guide to start when you begin using integration by parts. Okay, so you could go ahead and use this strategy, and let's go ahead and apply the strategy on a couple of practice problems. So in our first example over here, it says to evaluate the integral of x times cos of x dx. Very typical problem. This is integration by parts. How do I know? Well, one, we have a multiplication, and it's a multiplication of two different types of function. We have x, which is a polynomial function, or what we call an algebraic function, times cos of x, which is a trig function. So we're multiplying algebraic times a cos function. Well, if we think back to our strategy, we have LIATE. We're dealing with algebraic A and trig function T. So you have to identify your U. What is the U in this case? That's what you're asking yourself. Since A is above T, A is algebra, in this case X, T is cos, that means we're letting U equal X, okay? Notice that for U substitution, this was not allowed. We were not allowed to use a substitution U equals X because I told you it's not efficient, it's just you're wasting time. But for integration by parts, you may have to use the substitution U equals X, okay? So here it's fine. So we're letting u equal x, and we're letting dv equal the other function, cos of x. Okay, the other function that you're multiplying, cos of x, along with the dx, we're including him. Okay, so you always start off with u, dv, and now you're looking for du, and at the same time you're looking for v. This is the game plan. So I set it up in this fashion just to remember how to solve the problem. It's easier this way because we're going back to our initial formula that we memorized. The integral of u dv is equal to uv minus the integral v du. It's always based off this formula. So we identified in our case here, our u was the x. Let's do that here. This was our u, and whatever's left over was our dv. We called this our dv. Okay. Now that we identified u and dv, what we have to go get is our du and our v. How do we get that? Well, let's think about it. We have u, we want du. How do we find du? Well, at this stage here, you have to take the derivative. Okay. So here we're deriving with respect to x. What's the derivative of x? Well, it's just 1. And since we're deriving with respect to x, we get a dx. Okay. Next, what we have is v. How do we go from dv to v? Well, let's think about it. We have the derivative, we want the original function. How do we do that? Well, here we derive, here we integrate. So on the side, we're integrating. Okay. So what's the integral of cos of x? Well, we know the derivative of sine is cos, so the integral of cos is back up to sine. So here, to integrate, you get sine of x. Okay. And now we follow our rule. So we started off with u dv, which was x times cos of x dx, and now we want this piece here, u times v minus integral of v du. So essentially what you're doing is you're doing your u times v, so you're following this pattern. Top left to bottom right, u times v, we're multiplying these two terms, u times v, which is in this case x times sine of x, and then you're doing minus the integral of v, which in this case is sine, times du, which is 1 dx. So we go this way. So every time you do this, you go top left to bottom right, and then you go across to the left. So you always have this kind of formation. This is why I always set it up this way, because I remember the formula in this fashion. Okay, so following u times v, so this over here is essentially side work. This is something you do on the side. And then up here, following our formula here, what we get is u times dv is equal to u times v. So u is x times v, which is sine x, minus the integral, so we're following this, v in this case, v is sine of x, and du is 1 dx, which I'm just going to write dx. And we went from something which we were not able to integrate to now something that's simple to integrate. The x times sine x is on the outside of the integral sign, so we don't have to deal with them. All we have to do is take the integral of sine, which we know, because we know the derivative of sine is cos, so that means the integral of sine is negative cos. So we get x times sine x minus negative cos, which turns into a plus cos of x. And since this is a definite integral, plus c, don't forget that guy. And this is the final answer, okay? So let's go ahead and keep practicing. So in the next example, we have to evaluate the integral of x squared times e to the x dx. So let's go ahead and do that. First of all, we have a multiplication of two different types of functions. We're dealing with a polynomial function, x squared, times e to the x, which is an exponential function. So we're using, this is a polynomial function, or what we call algebraic function. So we're dealing with a, and e to the x is exponential, so we're dealing with e. Since a lies above e, x squared and e to the x, that means we have to let our u equal the x squared. Okay. So this is u, which leaves us with the rest, which is our dv. Okay. So e to the x dx is equal to dv. Okay. So again, we're just following this formula here. We have our u, we have our dv. And now we're going to transform it to u times v minus the integral of v du. Okay, so in order to do that, we need to go get du, we have to go get v. So to get du, we derive. We have u, we want the derivative, so we're deriving with respect to x, giving us 2x dx. The dx is technically here on the bottom, but we're essentially multiplying it up here, so we write it as du equals 2x dx. And the v we have to integrate. And this is easy because the integral of e to the x, we like it, is e to the x. Okay, so just remember this is derivative, derive, and this to this we have to integrate. Okay, so we're combining Cal 1 and Cal 2 in integration by part problems. Okay, and now we apply our formula here. So again, this is side work. This is stuff you do on the side. And from here, we continue down here. Using our formula, the integral of u dv equals u times v minus integral v du. Okay, so u times v, in this case, is x squared times e to the x. This is on the outside of the integral, minus the integral of v times du. So again, we follow this pattern of top left to bottom right, minus the integral of bottom right to bottom left. So minus the integral of 2x times e to the x dx. Okay, so I just moved the 2x over here in the front, and we're left with this. Okay, this is good, but it's not done. We're still stuck here. We have this issue of 2x times e to the x, and we have to integrate this. We'll notice that we're not finished, but it is simpler from what we started with. We had x squared times e to the x, and now if we take out the 2, minus 2, we take it out of the integral sign, we're left with x times e to the x, which is a simplified version of this. The x squared is 1 degree lower. So we just have to apply integration by parts again. So you could do this multiple times. So in this case, we have to do it twice. So we restart, we start the process over again, and now we apply it just on this piece over here. So let's go ahead and do that. Since we're doing it again, I don't want to use the same notation here. So I'm going to call it u, let's say bar, or call it something else. I'm going to call it u1 now. Technically, this should be u1, this is u2, but I'll call this u1 just to differentiate the difference between these two here. So u1 now, we'll call it x. Again, we're still multiplying an algebraic function times an exponential function, so algebra still stands above exponential, but in this case now we have not x squared, but x. Still above that, so I'm letting u1 equal x, which means that I have to go get my du1, I have to go get my dv1, and my v1. Okay, so I'm just using different notation, not to copy the ones here. Okay, so u1 is equal to x, dv1 is equal to ex dx. And du1, the derivative of x is just dx, 1 dx, and the derivative of, the integral of dv1 is again just e to the x. Very simple. So here we took the derivative, I'm going to write it this way, d dx, and here we integrate, which I'll just write with an integration symbol. Okay, we finish this piece, and now we apply our rule again, giving us x squared times e to the x. That piece was from the outside, x squared times e to the x, minus 2 times, and now in the bracket, instead of this whole thing, I'm going to write what it's equal to. So again, u1 times v1, or u times v, in this case it's x times e to the x, minus the integral of v1 times du1. Okay, so again, we have this pattern from top left to bottom right, minus the integral of bottom right to bottom left. So e to the x times dx. And now we reduced it to this, which is very simple to solve. We know the integral of e to the x. It's very simple. That's just e to the x. And we're essentially done. So let me just erase to give myself some room. And let's go ahead and write the answer. Okay. So this is equal to x squared times e to the x. Minus 2, I'm going to distribute it, giving me minus 2x e to the x. And now I'm going to distribute here, minus 2 times here becomes positive 2. And the integral of e to the x is just e to the x. And if you leave your answer like this, it's wrong. Be careful. It's a definite integral. Don't forget your plus c. So you could express it in this fashion, or if you want to go one step further, you could factor out an e to the x. Each term here has an e to the x. We could remove them, leaving us with e to the x, open bracket, x squared minus 2x plus 2. And don't forget your plus c. And that's the final answer. We're done. This is a plus c. Okay, so this is an example where we had to apply integration by parts twice in order to solve it. Okay, So very nice. Let's keep practicing and look at the next problem. So here we have example 3, evaluate the integral of ln of x dx. So pause the video, give this a shot, see if you're able to solve on your own. Okay, so what's difficult about this problem is that it doesn't look like an integration by parts problem, but in fact it is. So you just have to think of this as we have our ln of x times, let's say, 1 dx. Okay, so there is technically a multiplication here. You're just multiplying by 1, which we don't usually write, but you could think of it in this fashion. And applying LIATE, what should we call our u? Well, not much of a choice here. We have our u, we're dealing with the log function ln, so right away I know my u is going to be ln of x, right? Because we have a logarithm function and it's being multiplied by 1, which you could think of as an algebraic function, just like a polynomial x to the exponent 0, which is 1. So L is ln of x, and that beats my 1. So u is ln of x, dv, we're left with just 1 dx. We write whatever's left over, and we have to go ahead and find our du, and we have to go ahead and find our v. The derivative of ln of x is 1 over x dx, and the integral of 1 is simply just x. Okay, using the power rule. So now we apply our integration by parts formula. So it's going to be u times v. So this thing here is equal to u times v, which is ln of x times x, minus the integral of v du. In this case, x times 1 over x dx. Okay, and now this is simple to solve. Okay, because x times 1 over x, they cancel each other. We're left with the integral of 1. So very simple. X times ln of x minus the integral of 1 dx, which is simply just x times ln of x minus x plus c. And if you want, you could factor out an x, leaving us with x times ln of x minus 1 plus c, and we are done. This is the problem. Okay, so let's take a look at the next one. So here, example number 4, we have to evaluate the integral of e to the x times cos x dx. This one here is a very common trick. Be careful. Let's go ahead and solve this one together. So first, we have a multiplication of two different types of function. We're dealing with an exponential function times a trig function. Notice that these are basically the bottom dwellers of our LIATE. We have trig and exponentials. In this case, trig is cos of x and exponential is e to the x. Okay, so using our LIATE trick, we're supposed to let u equal the trig function because trig lies above exponential. But in this specific problem, e to the x times cos and e to the x times sine, or any variation of those guys, it actually doesn't work. This is one of the cases where our strategy doesn't work. Okay, so I want to show you guys that. In order to solve this problem, we get it with letting u equal e to the x, the exponential. And it's weird because typically when you let your u equal something, when you take its derivative, it goes down. We saw an example where we had x squared times, I believe it was e to the x, and we had to use integration by parts twice, because when we took the first derivative, we reduced it from x squared to a 2x, and then we went again, and then it eventually canceled out the x squared term. So eventually, after taking the derivative multiple times, one of the terms cancel. The issue with e to the x and cos of x, or e to the x and sine or cos, when you take its derivative, especially e to the x, it stays the same, it doesn't disappear. And sine and cos, we know there's a pattern. So when you take the derivative of sine, you go to cos, and then cos goes to negative sine, then negative sine, negative cos, and then back to where you started. So in both cases, when we take the derivative, our functions don't disappear, and this is an issue. But we could get by. Okay, we just have to be a bit clever. Let's go ahead and see how. So we begin by letting u equal e to the x, and we let dv equal what's left over, in this case cos x dx. Okay. Now we go ahead and we solve for du, and at the same time v. The derivative of e to the x is e to the x dx, and the integral of cos of x, so the derivative of sine is cos, so the integral of cos, we saw this earlier, was sine of x. Okay. So let's go ahead and apply our property. We know that the integral of u dv is equal to uv minus the integral of v du. So this thing over here comes in as u times v e to the x times sine of x minus the integral of v du. In this case, sine of x times e to the x dx. Okay, but this is an issue. We again have a trig function, sine times e to the x, similar to what we started with, but instead of cos now we have a sine. How do we deal with it? Well, we have to use integration by parts. Again, we're just going to focus on this integral over here in square brackets. Okay, so let's go through the process again. I'm not going to use the same letters, I'm going to change it up, so I'll call it, let's say, u bar or u1 or something, or u tilde. Just change the notation, don't use the same one. And we're going to not apply LIATE again, we're going to let it equal e to the x. It might seem like I'm wasting my time, but it actually does work out. So u1 equals e to the x, dv1 is equal to sine x dx. Notice that whenever you have derivatives, you have du and dx. Here you have dv and dx. It's always written whenever you have u, there's nothing, and when you have v, there's nothing. So just be careful with the notation. So here u has nothing, dv1 has dx. But when I take the derivative of u, du1, I get e to the x dx, okay? Because we're deriving. And for v1, I'm integrating the derivative, so we don't have the dx anymore. So the derivative of sine is cos, so the integral of sine is negative cos x. And we follow the same pattern. So here, what we have is e to the x sine x, that's still there, don't forget him. E to the x sine x. We have a minus, so minus the integral, minus, and now this integral here, we're going to rewrite it using the fact that the integral of u dv is equal to uv minus the integral of v du. So this is our u, this is our dv. So we go from top left to bottom right, so e to the x times negative cos x. This is a multiplication, minus the integral of v du. So this is going to become plus because we have a negative, and then we have cos x e to the x. Okay, so again, we're stuck. This doesn't seem like we're progressing. So why are we doing all this? Why is this a good thing? Let me erase and all the middle work and convince you why this is a good thing. Erase all this, and let's just rewrite this whole thing up there. So we started off with this thing and we said it's equal to this. Well, this thing here is just the integral of e to the x cos x dx. And what we have here is e to the x sine x. We have a minus over here, so it's going to distribute and cancel with the minus that's over here, leaving us with plus e to the x cos x. And then this minus is going to distribute and turn this into a minus, giving us minus the integral of, let's say, e to the x cos x. Multiply here, cos x times e to the x is the same as e to the x times cos x, because 2 times 3 is the same as 3 times 2, so you can flip their order. What you have to notice here is that this thing here is the same thing as what we started with. So essentially what we can do is take this and bring it over on the other side. Since it's a minus here, it goes over as a plus, so you're going to have two of these things. So what we get is 2 times this integral, e to the x cos x dx, is equal to this thing over here. I'm just going to factor out the e to the x of sine x plus cos x. Okay, so this integral over here is equal to this thing over here, but there's 2 of them, so let's just divide it by 2. So we end up with the integral of e to the x cos x dx is equal to e to the x sine x plus cos x divided by 2. And since it's a definite, integral plus c. And this is our answer. This is the final answer. So this is a nice example where it looked like we were in a loop, but it ends up working out, where you have to go back to where you started, okay? So notice when we apply LIATE, and you end up with 2 functions, which are the bottom 2, this is the trick you have to apply, okay? Trig and exponentials. So let's go ahead and take a look at our final example. So in our final example over here, it says to evaluate the integral of sine to the square root of x dx. So go ahead, pause the video, give this a shot, see if you're able to solve it on your own. This over here is actually a bit of a trick. So it might not be the only way of doing it, but what I'm seeing right now is to begin by actually applying a u substitution first. You might have to use a u substitution first, and you might be able to get away with it without doing this at all. Okay, but the first thing that I see is to let u, we're applying a u substitution from our previous video. I'm going to let u equal square root of x. I'm just going to write it as x to the 1/2. And let's take the derivative of this. So we're left with 1/2 comes in front, x to the minus 1/2, and this is the derivative dx, giving us du over dx is equal to 1 over 2x to the 1/2. And solving for dx by cross multiplying, we get 2x to the 1/2 du equals dx. Okay, so this is our u substitution, and we could rewrite this in terms of u by substituting the square root of x, because this is square root of x, with u. So we have sine of u, and we're replacing dx with 2x to the 1/2 du. But this is an issue. We have an x here to the 1/2. We have to express this solely in terms of u. We know this from u substitution. Well, x to the 1/2 is actually our u. So this could be expressed as, I'm going to remove the 2 because it's a constant in the front, and we're left with just u times sine of u du. And we've reduced the problem to something that's similar to what we started with. Notice the first example that we had was x times cos of x. This is essentially the same thing, but now it's u times sine of u, but it's the same game plan. We're going to apply integration by parts at this stage here. So there might be examples where you have to combine u substitution with integration by parts, such as this one. You might not have to do it, but it might be a possibility in order to solve it. So let's just move this, and now let's start our u substitution. Our integration by parts. So having done the u substitution, I'm just going to call this now u1. So u1 is the algebraic function, so this is algebra. Let's do this in red. This is the algebra function, or the polynomial, and this is a trig function. We know that algebra is above trig because LIATE a before t. So we let u1 equal, in this case, u, and we let dv, let's call it dv1, equal whatever is left, sine u du. Du. Now we take the derivative with respect to u, which gives us the derivative of u is just 1 du, and our v1 is equal to the integral of sine, which we know is negative cos. Again, we're all in terms of u, okay? Because we're not using the variable x, we're using the variable u now, having done a u substitution earlier, okay? And recall the u substitution that was done earlier, let me just write it on the top, was u equals x to the 1/2, or square root of x. Now from this we apply our rules, so this is side work. We continue from here now. This is equal to, the 2 is still in the front, and the integral of u dv becomes now u times v, or top left times top right. So u times negative cos of u, negative u times cos of u, minus the integral of v du. So negative cos u times 1 du. The two negatives turn this into a positive, and we're left with integral of cos u du, which we know how to integrate now. This over here, the 2 multiplies in, so we get negative 2u cos of u, plus the 2 multiplies to this guy as well, and we know the integral of cos is sine u, and plus c. Okay, so here's an example where we have to apply a u substitution with an integration by parts. But stopping over here is wrong. Remember, we started in terms of x, we finish in terms of x. Can't leave it in terms of u, so what do? We go back to our original substitution and bring it back in terms of x. So instead of writing u, we're going to replace them with x to the 1/2, or square root of x. So this is equal to negative 2 square root of x times cos of square root of x plus 2 times sine of square root of x plus c. If you want to factor out the 2, that's fine, but you can leave your answer like this. This is the final answer. Okay. So I hope this video helped. I hope you have a better understanding of integration by parts and how to apply it. Make sure to memorize your rule and the setup. Okay, so wish you guys the best, and I'll see you in the next video. Take care.